So now we are going to talk about near-infrared spectroscopy in order to study the quality of fruit and vegetable. So we are two speakers, Audrey Pissard from research in agronomy in Gembloux, in Wallonie, and me, Sylvie Bureau from INRAE at Avignon. Strange. You see my second slide?
Yes,
Yes.
it's
Yes.
not in full screen, but we see it.
Yes. So during this course, we will have 3 parts. So the first on near-infrared spectroscopy and the principle of using this technique. The second part on data treatment. And the third on some examples we perform at Gembloux and at Avignon. Before starting, just a few words on fruit quality. It's a complex concept because it depends on different quality traits, for example, texture, with different range between hardness and softness. And we can speak about viscosity after processing on puree, for example, on fruit puree. The taste with sweetness, acidity, and aroma, color. We have a difference between unblushed and blushed side on fruit, for example, and some fruit with color from green, yellow, orange, red, and some problem of browning during processing. And health with the intake of fibers, micronutrients, and low calorie density when we eat fruit. And in this talk, we will focus on organoleptic and nutritional quality also. These quality traits evolve during maturation, during storage, according to the temperature or to the atmosphere, and during processing. By heating, you involve some big change on fruit. So as I mentioned, the food quality is very complex. So to measure the food quality, we need a larger kind of equipments. And here you have some equipments to measure texture or rheology, to measure color with a chromometer, to measure dry matter using oven, to measure soluble solid contents or acidity using a refractometer or titrator, and to measure sugar, organic acid, polyphenols, carotenoids, and volatiles. We can use some equipment such as chromatography to separate each compound in order to measure each other. And now we will see the interest of using NIR to measure food quality. So in the first part, so the near-infrared spectroscopy, it's based on the measurement of the interaction between infrared radiations and sample. And here we will speak about food measurement. Is it okay for my slides? Yeah. Here the electromagnetic spectrum, and which is divided in different area, and each area can have an analytical skill. Each area is characterized by a range of energy, frequency, and wavelengths. And here we will speak about near-infrared. Can I add my... You see my mouse or
Yes.
not? Yes. So the talk here is focused on NIR, so between 800 nanometer and 2500 nanometer. And the infrared spectroscopy is the region characterized by the vibrations of molecular bonds. So when the frequency of the radiation, so of the infrared radiation, is equal to the proper frequency of the band vibration, the energy is absorbed and the band vibrates. So here, in food, the main compound is water, and here you can have different kind of band vibration due to infrared spectroscopy. And the results of this vibration is a spectrum. So the measurement in infrared radiation is a non-destructive and a rapid measurement. So directly you can measure fruit. The result is a spectrum, which is the addition of all vibration of bonds of compounds present in the fruit. So the spectrum obtained is specific of the quality and properties of the measured fruit. It's not an apple, but an apricot. And in fruit in general and apricot in apple in particular, the main compound are water, sugars, and organic acid. So the spectrum will be specific of this compound. In NIR, the beam penetration is around 0.5 to 1 centimeters. It can vary according to the fruit or to the equipment. And the penetration is enough deep inside the sample to have enough information we can use to define the fruit quality. According to the equipment, the measurement could be a diffuse reflectance, so there is an angle of 45 degrees between the incident beam and the reflected beam, or the measurement could be in interactance, and there is no angle between incident and reflected beams. So this kind of measurement could have also an effect of the beam penetration and the information you can obtain. Now there are different kind of tool in near infrared, some big machines such as like this. You can have to sort fruits according to their internal quality, and you can sort fruits according to their sugar content, for example, and to separate fruits ready to eat, or fruits could be stored for some period. Some equipment we have in research lab, and some other equipment put on agriculture machine, or some very small and portable equipment we use to measure directly fruits in orchard. So a large range of equipment to measure in NIR. There are lots of scientific papers on NIR in food concerning, for example, the animal sector. NIR could be used to determine the fat content in meat, or the detection of meat flour in feed. NIR is used also in for plant. So, for example, to map the protein content in field according to the location. For apple, to estimate the maturity stage in orchard. Some application in the milk industry, and here an example of yogurt to follow the fermentation in real time, or in other agricultural produces such as coffee or honey, to determine, to authenticate, for example, the origin or the fraud detection. There are a lot of frauds in honey, for example, by adding sugar, and you can use INRAE to detect the sugar addition in honey. For fruit and vegetable, yes, there are also lots of paper on a large range of different fruits and vegetables, but the main paper concerns apple, tomato, grape, olive, peach, kiwi, pear, and melon. And the quality traits measured by INRAE are dry matter, soluble solid content, acidity, starch content, oil content in olive, for example, and evaluate damage which are not yet visible. So to detect damage before, to sort fruit before damage are visible. For the part 2, so now Audrey?
Yes, thank you. So I will present you the second part concerning data treatment, or also called chemometrics. So the aim of chemometrics is to extract the useful information from complex data using statistical and mathematical methods. The idea of this part is not to enter into detail into chemometric, but to give you an idea of the data treatment. But if you are interested in chemometrics, here in CRA, we organized every year an international training on spectroscopy and chemometrics. So if you are interested, don't hesitate to contact me.
Yes.
Yes, sorry. So NIRS is an indirect method, so other data are needed to do quantification or discrimination. Spectra only are not or few informative, so other data are needed. There are two main kinds of data. There are qualitative data, for example, the acidity content, the Brix content, etc., coming from the chemistry. And there is also qualitative data. There are known information from an experimental design, for example, the year, the species, and the varieties. And these information are used to make discrimination. For quantitative purpose, you need to develop a calibration model or an equation. This is done in 2 steps. The first step is the calibration. So the idea is to develop a calibration model with the spectra and the reference value coming from the chemicals, the chemical analysis. So the aim is to establish a relation between the spectra. So they are the independent variable, the X, and the variable to predict, the Y, which is also called the dependent variable. Generally, we multiple linear regression are used, and also we use an internal validation. Generally, to perform the internal validation, we use a set of the data. We can use 2/3 of the data to do the calibration, and the remaining third is used to do the internal validation. There are different types of regression. Linear regression, for example, PLS, MLR, PCA, and PLS, donc the partial least square regression, is often used. There are also other type of regression or algorithm for nonlinear or more complex data, for example, SVM or random forest. So that's the first step is the calibration. Then the second step is the prediction of unknown samples. So you have unknown samples, you have new sample, and you will apply your model on this sample, and then you will have your prediction. So they are the predicted value. And then by comparing the predicted value with the measured value, you will have the performance of the model. So the performance of the model are generally evaluated with different statistics. There is the R square, so it's the coefficient of determination, and it is the proportion of the explained variability of the model, and it must be as high as possible. Then you have the RMSE. It's the root mean square error, is the estimation of the error of the model. And of course, it must be as low as possible. And finally, you have the RPD. It is the ratio of performance to deviation, and it gives an idea of the prediction accuracy. And generally, it is known that the prediction of the precision of the model is good if you have an RPD higher than 2.5. Then for discrimination and classification purpose, there are two kinds of methods. There are non-supervised methods, which means that only the spectra are used. So you will take into account only the spectra. For example, you have the principal component analysis, which allows to represent the data in a reduced space while preserving the maximum variance. For example, here, it's a PCA realized with so mid-infrared spectra of apple powders, and it shows that the two first PCs, so PC1 and PC2, allow to differentiate the different types of apple. So you have the dessert apple in green and the cider varieties in red. Another kind of non-supervised method is the hierarchical classification. And in this kind of analysis, the idea is to cluster the sample the most similar on the basis of the spectra. And here you can see that you have two big clusters corresponding to sample grinded without and with oxygen. These data are from INRAE. Then there is also the supervised classification method. And in this case, you will use the spectra and the information related to the spectra to perform the analysis. Here, for example, you have the factorial discriminant analysis from INRAE, and you can see in the graph that the samples are classified into groups according to criteria, and here in this case, it is the year. So the advantage of near infrared is spectroscopy is a rapid method. It's easy to use. It's non-destructive. It's a green method. When you have developed your model, you don't need any more organic solvent. It's a multi-parameter analysis. So with only one scan, you can predict several parameters. It allows you to make quantitative and qualitative analysis. You can measure a large number of samples. You can measure different kind of samples, so liquid, solid, and powder. You may use near spectroscopy in laboratory, but also in industry, in field orchards, etc. And it's also possible to link different instruments in a network within a factory, but also at a larger scale. There are also some drawbacks of NIRS. The first drawback is the need for reference data. So to develop your calibration model, you need chemical data for the parameter you want to develop a model. You need to develop specific calibration for each product and each constituent. For that, you need to establish a reliable collection of spectra and reference data. So you need to have qualitative spectra and reference data which are reliable. And finally, NIRS is not suitable for the determination of trace, residue, and mineral compounds. So it is known that you can measure major constituent and it's not possible to predict minor constituent. Now,
sorry, Audrey, perhaps there are some questions or we can continue.
Maybe you can continue and they can ask questions at the end.
Okay.
Okay, thank you. So now the third part concerning some examples of work performed at CRA on apple and at INRAE on apricot. So I will present you briefly the application of NIRS on fruit at CRA-W. This work results from a collaboration between two units, the Quality and Authentication of Product Unit managed by Vincent Batten and the Biodiversity and Plant and Forest Improvement Unit managed by Mark Latter. Just some words about the Quality and Authentication of Product Unit. To say that the unit has a large expertise in vibrational spectroscopy. We are working for 40 years on this topic, and now we have more than 35 instruments in the unit. Of course, we have near instruments, benchtop instrument, and also handheld instrument, but we have also mid-infrared Raman spectrometer and also hyperspectral imaging. For 2 decades, so since 2004, we are working on fruit and especially on apples. We worked on different projects aiming to determine the quality parameters, but also the optimal picking dates using near spectroscopy. So the main instrument we use and we are still using is the FOSS instrument, the XDS from FOSS, so which cover the visible range, but also the full range of near infrared. Then we evaluated different handheld instruments. So first we evaluated the Phasir, which is a quite big and heavy handheld device. We worked also on the diameter, which is not a spectrometer, but it's an instrument which gives you an index, which is the difference between the absorbance at two wavelengths. This index decreased during ripening, and it's a quite interesting instrument, but the drawback is that you have to determine specific value for each species and each cultivar. Then we worked on the micronear, the VAV, which is an ultra-compact spectrometer. And we test also the CRA-W, which is a pocket-sized spectrometer to be used with an application on a smartphone connected to a cloud, which gives you a real-time prediction. And finally, and now we are evaluating the Felix instrument. I will talk more about this instrument later. So with the data coming from the different projects, we constitute an Apple database with the spectra from the XDS. So you can see the different projects we had in the past and the sample number we measure. And actually, currently we have a database of more or less 5,000 of spectra. What we call a database is a set of spectra and the corresponding data. In our case, the data are constituted of chemical value. They are so coming from chemical analysis. And the parameter concern firmness, Brix acidity, vitamin, phenolic content, starch, and also strafe index and the index from the diameter. And since last year, we began to insert all this data into WholeSpec, which is a centralized database here in CRA. But I will talk about this later in my presentation. With the data from the XDS, we developed a calibration model for different parameters. So you can see the different parameters are maturity, the firmness, the Brix, the acidity, which are common and classical parameters, but we also developed model for total phenolic compounds, the index from the diameter and the strafe index. And as you can see, we had quite good results for the maturity, the Brix, the polyphenol, and the index from the diameter. In a previous project, we also worked on the vitamin C, and we tried other algorithms like SVM, and we developed a quite good model for the determination of the vitamin C. As I told you, we test and evaluated different handhelds on apples. And so here are some results for the prediction of sugar content using PLS regression, using the spectra from different devices. And as you can see, based on the RPD, you can see that the micronear give very good results, similar than those obtained with the XDS. At the opposite, the Phasir and the CRA-W gave a poor result. So for now, we are working especially with the Felix instrument. We acquired two instruments some years ago. We test pre-programmed model for apples, but we saw that this model were not suited, and so the idea was to collect spectra in order to develop our own models. So in the framework of the INRAE project, we collect spectra from a wide range of varieties, and also reference value for dry matter, firmness, Brix acidity, and total phenolic content. And we use the software from the Felix instrument, which are data viewer and model builder. So now we have a quite big database of spectra from the Felix, and now the idea is to exploit all this data to develop our own model and to integrate this new model into the device in order to be able to use the device directly in the orchard. Just a remark concerning the Felix. With Sylvie and the INRAE, we try to put together spectra from INRAE and CRA, as the idea is to share our data with the different partners. And we face the problem of the different version of the model builder. And so it's a drawback with Felix is that according to the different version, we have different software, and it seems difficult to merge the data. Last point concern the database constitution, which is CRA-W. It's a big project we have here in CRA. It's to develop a centralized database gathering all spectra from all devices for all products. So schematically, you can see here the CRA-W project. So you have the spectra from the different devices. These spectra are stored on a server with the data related to the spectra. Then we have developed a software which is called Pool Spec Manager in order to manage and to insert the data into the database. Besides, you have a website which is called CRA-W Explorer, which allow you to search for data. For example, you can search for specific spectra. For example, you can search for spectra for apples. So you have to select the. Here it's a little bit little so you can read, but normally you have to select the product, which is food product. Then second is the fruit, and second it's and after is the apple. And you have also to select from which device you want the spectra. For example, here it's the spectra from the XDS. And then the website, which will give you the data in a CSV format, and you can use this data with the software you have to analyze the data. That's the global idea of the CRA-W device. For apples, as I told you, we have insert the historical database, and we are also inserting the new data. And this is done for the spectra of the different device, the XDS, the Felix, and the VAV. And so the idea in the InnoBridge project is also to be able to insert data from the partners.
Thank you, Audrey. So I will continue on a project we had in collaboration with an experimental and technical center in France. And the objective of this project is to use a handheld INRAE to determine non-destructively the apricot internal food quality directly in orchard. For the context, consumers are less and less satisfied with the apricot quality, and it's probably due to bad quality in relationship with the food harvesting, too early or too late, and high heterogeneity in food batches. And in the same time, it's becoming more and more difficult to determine the optimal harvesting date because of the coloration of peel. And in general, as you can see here, the red coloration turns very early during maturation and before the physiological maturity of fruit. So it's complicated to determine the optimal date. So it's the reason why the INRAE could be very interesting for assessing the internal food quality. So the aim of this project is to use a portable spectrometer. So in this project we use the Felix equipment, as Audrey mentioned, to predict soluble solid content and titratable acidity in apricot. Concerning samples, so a large diversity is taken into account with 28 varieties over 4 years, so between 2019 and 2022. It represented about between 10 to 16 varieties per year, between 20 to 30 fruits per varieties, and 2 spectra per fruits on the opposite sides. And in total, more than 1,000 fruits were measured. So spectra were acquired with the Felix instruments in the range including the visible and the very beginning of the INRAE region. And in the project, we use 4 different tools, not only one. And the reference measurements were soluble solid content and titratable acidity. Concerning the soluble solid content and titratable acidity, a large diversity was observed. For soluble solid content, the range was between 6.2 to 22.6 degree Brix, and for titratable acidity, the range was between 4.5 to 46.8 milliequivalent per 100 gram. So the data were very variable, so the data set was very well adapted for testing infrared tools. Concerning spectra, the exploratory analysis of spectra illustrates the interest of using pretreatment on spectra before analysis. As you can see here, before, without any pretreatment, the effect of the different tools and different years were very predominant. We can discriminate each tool and each year. But after pretreatment, in this case, we used second derivative, all data are in the same cloud, a very large cloud, but in the same cloud for the different tools and different years. So it appeared necessary to apply pretreatment before spectral analysis. Concerning models, so in the today I choose to show you only the model obtained with all data, so including data from the different tools and from the different years. And the results obtained for soluble solid contents were very good, with the R square of 0.9, RMC of 0.86, and RPD higher than 3. The results were not so good as for soluble solid content, but they are in line with results obtained in literature. And it's a general observation. The data obtained for tetratable acidity were always lower than those we can have for soluble solid content. And these results were not so far from results obtained with a benchtop spectrometer, some results we had a few years later. So we decided to use these models, so multi-year and multi-tools models, to see if it's possible to monitor fruit changes during their ripening on trees. So the models were tested on Ladycot and an apricot variety in 2022. We used a Felix instrument. Measurements were done twice a week on trees and on the most accessible side of 50 apricots, so like this. And models made it possible to predict soluble solid content and titratable acidity in a realistic way. And at the end, the same apricot were both characterized by INRAE and by reference data for soluble solid content and titratable acidity here. And the values were very close between predicted by INRAE and measured by reference methods. So with a portable spectrometer, we are able to have a good prediction of soluble solid content and titratable acidity on apricot. And this work using Felix spectrometer is continuing in the INOBRID project in a task dedicated to the non-destructive fruit quality screening. So we will continue to use INRAE on different fruit species: apple, pear, apricot, peach, and citrus. Using a large panel of representative varieties according to the countries and to the partners. And fruit are characterized at harvest and after a period of post-harvest, so a few days, for example, for apricot at a room temperature, or after several weeks for apple with cold storage, for example. Different tools are used, not only Felix portable instrument, but also benchtop instruments. And according to partners, we have different instruments, so we will continue to use them. And after we will try to to treat the data and develop some models. And concerning reference measurement, we decided to measure firmness, color, soluble solid content, titratable acidity, dry matter, and for nutritional traits, fibers, polyphenols, and starch. And as mentioned by Audrey, the objective is to build common database to put together all data from the different partners and different species in order to build a database very rich, because including a large food variability, and second, to build robust model per species in order to predict the food quality. So it's the last slide. So thank you for your attention. And if you have some question,